Okay, so now I would like to discuss a topic that actually doesn't appear in the notes, but it's important enough that I think that we should discuss it. And this is called Noether's theorem. Noether's theorem is named after Emmy Noether. Emmy Noether is certainly one of the most famous mathematical physicists who were female. Emmy Noether was Jewish. She grew up in Germany. At the time of the Second World War, she had to leave Germany and move to the United States. So the first part of her career was spent in Europe, in Germany, and the second part of her career was spent in the United States. She was very famous. She knew Einstein, for example, and she proved this beautiful theorem that we're going to discuss now, really one of the most important theorems in physics, I would say, very, very deep. But she also made very big contributions in pure mathematics in the field of algebra. You might, in your reading, come across things called Noetherian rings, for example. Well, this was, again, part of Emmy Noether's contribution. Okay, so what did Noether's theorem tell us? Well, it says for every continuous, okay, so that's an important word, continuous. For every continuous global, another important word, for every continuous global symmetry, there is a conservation law. This is a very deep theorem. So let me explain to you, let me give you some indication of why it's deep. Let me justify that comment. Well, when you think about classical mechanics, many of the ideas in classical mechanics don't survive to quantum mechanics. In particular, in classical mechanics, we measure positions and velocities of particles. In quantum mechanics, you can measure the position or the velocity, but not both. If you move to classical field theory, again, many concepts don't survive, and in quantum field theory, even fewer concepts survive. So that's telling you that the concepts that you were dealing with were not very fundamental. Noether's theorem holds in classical mechanics, in quantum mechanics, in classical field theory, and in quantum field theory. So that should give you some indication that this really is quite a deep result. We will study Noether's theorem in classical field theory, okay? But you know it holds in all of these other cases. So let me put in brackets here, classical field theory. But you know it holds in all of these other cases too. And in classical field theory, what does it say? Well, Noether's theorem is the statement that d mu, j mu, is equal to 0. So let's unpack this quantity, this equation a little bit. What we've got here is J mu. J mu is our conserved current. Conserved current. It's a 4 vector, so there are 4 components in it. This first component, which is rho, we call that the density of this conserved quantity. And we call J the current of this conserved quantity. Now, any quantity that is conserved will have a current associated to it. So we know electric charge is conserved, so there'll be an electric current. And rho would be the charge density, and J would be the usual electric current. But other quantities that are conserved also have this description. So for example, if you think about momentum, there will be a momentum density and a momentum current. If you think about energy, there will be an energy density and an energy current. So every quantity that is conserved is associated to a current J mu, a conserved current J mu. What is the statement that J mu is conserved? Well, it's that boxed equation. And if I write it out, it says d rho dt plus the divergence of J is equal to 0. Okay? So that is exactly the same as the first boxed equation. That's the statement of the conservation of this quantity. And this equation is often called the continuity equation. Okay, good. Now, you might ask yourself, what is it that is conserved? Well, the conserved charge, so you know, you're used to thinking that the conserved charge is just a number. So how would I get the conserved electric charge or the conserved momentum or whatever else? So let's just call it Q. So this would be an integral d3x of the charge density. So for example, if I wanted to get the momentum, there would be some momentum density that I would integrate. And where do I integrate this over? Well, I integrate it over V. And what is V? V is the entire, let me call it spatial universe, okay? So freeze time, and then allow X, Y, and Z to vary. That entire domain of X, Y, and Z, that's what I'm calling the spatial universe. So let's check that this charge is conserved. I think that you're used to writing for the conservation of charge that dq dt should be 0. So let's calculate what dq dt is. So if I want to calculate dq dt, well, I've got this expression for q as a volume integral. So I can take the derivative into the volume integral d3x of v. Now, when I've taken the integral d3x of rho, I get something that just depends on t, but rho itself depends on t, x, y, and z. So when the derivative acts on rho, I only want to hit the t variable, so it becomes a partial derivative. Now, using the continuity equation, so let's maybe give the continuity equation a number. Let's call it number 1. And for this equality, what I'm going to do now, you should use the continuity equation. What you get is you get minus the integral d3x over v of the divergence of the current. I just solved 1 for what d rho dt is, and it's minus the divergence of the current. For the next equality, well, this is easy. I can just use Gauss's theorem. Gauss's theorem tells me that the integral over the volume of a divergence can be written as the integral of the quantity whose divergence you're taking dotted into a little area element, and we should integrate over dv. So what dv is, this is the surface bounding v. Okay, so it's just the boundary of v. So if v was this room that you're sitting in right now, what would be the boundary of v? Well, it would be the roof, the floor, and the walls. Okay, so that's what dv is. It's just the boundary of v. And dA is a little area element so that you can integrate over this boundary. Okay. Now, where is the surface that's bounding V? It is located at spatial infinity. And as usual in quantum field theory, we imagine that at spatial infinity, our fields vanish. And in particular, our current will vanish. So we're just integrating 0 over the surface, and we get 0. So now we've got a second statement that we've just managed to prove, which tells us that dq dt is equal to 0. Okay? And it's the second statement that you might have been more familiar with if you were thinking about a conservation law. It's the second statement that we would obtain if we were doing classical mechanics. By the way, when you do Newton's theorem for classical mechanics, you will get equation 2. if you work out Newton's theorem for classical field theory, you will get equation 1. So it gives you the correct conservation law for the correct theory. But we've got two conservation laws, 1 and 2. Why the difference? So let's say why are there two possible conservation laws? Now, we showed that 1 implies 2. We showed that 1 implies 2. But in actual fact, what we're going to show now is the equation 2, just dq dt is equal to 0, is not good enough. Okay? It's not a correct way to state the charge is conserved. You must use equation 1. And what is the reason for this? It is because the speed of light is finite. So that's what I want to explain now. Okay? So let's see how that goes. By now, I think that you should be getting used to the arguments, and it shouldn't surprise you too much at all. So I'm going to start off by drawing a space-time diagram. So here is t, here is x, and what I'm going to imagine that I've got two charges, okay? And I'm going to draw the world lines of the charges. So the one charge, which is a charge of q, it propagates along the world line that I've drawn. I've got another charge of minus q that propagates along the world line that's drawn. And at time t is equal to 0, these two charges disappear at the exact same instant. So what does that mean? Well, an observer living in this frame, before time is 0, if you add up the total charge, you get 0. After time is 0, if you add up the total charge, you still get 0. So these two world lines are perfectly consistent with dq dt is equal to 0 in, let's say, the tx frame. Okay, so this, if this was our conservation law, we'd say this process that we see here is perfectly allowed, no problem. Okay, now let's change frames. Okay, so I want to move to a boosted frame, and let me draw on the boosted frame. So here we go, here's time t prime. Let me draw in x prime. There's the spatial position x prime. And I want to draw some lines of constant time, okay? So on this original picture, you know, what are the lines of constant time in the tx frame? Well, there are these thin lines that I'm drawing over here. And if you were to sit on any of these thin lines, that corresponds, all points on that thin line is at the same time t, and you can see that the total charge on any of those thin lines is 0. Now let's do the same for the primed frame. So again, I start drawing lines which are parallel to the x primed axis. And now what you can see is, look, for example, at this line over here. At this line over here, so I'm looking down at this line, you can see that the charge minus q has already disappeared, but the charge q has not yet disappeared. So even though the charges disappeared at the exact same instant simultaneously in the tx frame, it turns out in the t prime x prime frame, charge minus q disappears before charge q does. So in the tx prime frame, we find dq dt prime is not equal to 0 in the t prime x prime frame. So what we learn is our equation number 2, which is dq dt is equal to 0. So equation 2 is not a Lorentz invariant statement. If it's not a Lorentz invariant statement, different Lorentz frames do not agree that this is a true statement. So observers in different Lorentz frames do not agree. So this means this is not a suitable law of nature. Sorry, that conservation law is not allowed. But look in contrast at equation 1. Well, our equation 1, so this is equation 1 as well, is d mu, j mu is equal to 0. But that is Lorentz invariance. We have contracted two 4-vector indices. So 1 is Lorentz invariant, which implies it's a perfectly good law of nature. And that's why we have to use equation 1. Just to come back to the physics a bit, what does this mean? Well, it means the following. So here we had just the two charges disappearing. But let's imagine rather that charge Q came towards minus Q, and charge minus Q came towards Q, and they met and they disappeared at this point over here. This would be perfectly consistent with equation 1. You see, equation 1 is telling us if the charge density changes, so if d rho dt is non-zero, it's because the divergence of the current is non-zero. It's because an electric current flows. So for the charge density to change, an electric current must flow. So here, the two charges flowed towards each other. When they got to the same point, they annihilated. And you see, if this happened at a point, then it's happening at a point in the Tx frame, and it's also happening at a point at the T prime X prime frame. So if the two charges flow to a single point and disappear, all Lorentz observers will agree that that's what happened. They're not going to agree at what point the two charges disappeared, but they will agree that the two charges disappeared at the same point. And that means all Lorentz observers will agree that charge was conserved. Great. So now we know why we're shooting for the kind of conservation law we're shooting for, why we're shooting for something like equation 1. Let's get started with the proof of Newton's theorem.